Okay, are you guys with me?
Yes.
Hello, can you guys hear me? Okay, okay.
Yes, we can hear you.
We can get
So we're going to start despite us. All right. So we're going to start. We're going to start despite the fact that we are only 12. I guess the others will join us. Let's see if they have any intention of joining us. So we are still doing calculations. As I told you yesterday, we're just deriving formulas and expressions for the velocities and accelerations. So yesterday we did some velocities and accelerations. I think ended on the acceleration on coordinate cylindric. We calculated the acceleration and we had this expression here. And if you guys had revised that, I'm sure you know where it's from. And if you did the work I gave you guys, by the way, only one group has sent me their solutions, unfortunately. So if you had done like I gave you, I'm sure you would have practiced how to find velocity and how to find the acceleration. I'm sorry about that. I'm having some technical problems here. The Wi-Fi is performing. I keep getting disconnected. Are you guys with me now? I'm sorry about that.
Yes.
Yes. Yes, we can.
Okay, lovely. So yesterday we found the vector vitesse du repère Frenet. We found le vecteur vitesse du point M par rapport au référentiel R égale ds dt suivant le vecteur unitaire T. So c'est T qui est le tangente. Yeah, so we calculated this, we saw where it came from, so we have the vector vitesse as that one. And as we know already, for us to find the vector acceleration, we are going to have to derive the vector vitesse, and it's what we are going to do here in the coordonate, or bien dans le repère represents the acceleration, because I did mention that. We have gamma de point M par rapport au référentiel R égale dv dt. Oui, la vitesse du point M dans le référentiel R, ou bien par rapport au référentiel R dt is equal to, we found this yesterday, we found this ds dt. ds dt we said is equal to v, the magnitude or the module of the vector vitesse gives us the s sur dt. And I told you guys, don't forget that in the coordinate Frenet, the module of the vitesse or the magnitude of the vitesse gives us the s sur dt, la dérivée de l'abscisse curviline par rapport au temps. The s dt gives us the magnitude of the vector vitesse. So since we know that vector vitesse du point M, le référentiel R, dans le repère Frenet is equal to ds sur dt suivant t, that ds over dt can be written as v in short, because we have seen there that that's the magnitude of the vector Vitesse. So instead of writing ds dt, we just write v. That's why here we have a dérivé de vt par rapport au temps. Okay, that's why we have this here. And then we have two variables. Now we have this v varying, and we have the vector unitaire t varying also. So as usual, we are going to use produit, the produit, the product rule. So we are actually going to derive v par rapport au temps, keeping the tangent constant. Then we say plus, we keep v this time constant, and we're going to derive vector unitaire tangent par rapport au temps. So now we just have to develop these two terms that we have in our derivé. So now they are telling us S de t étant l'abscisse keveline et t varie suivant S de t. Do. So I don't know if you guys have understood that statement. S is the l'abscisse keveline, and yesterday we said l'abscisse keveline is the distance, the point M. Once more, I apologize for that. I'm very sorry for the connection losses I'm having. I don't know, it's like the Wi-Fi also doesn't want us to learn today. But I have switched to using the internet cable, so I hope the connection will be more stable now, inshallah. So I was talking about l'abscisse keveling. And yesterday we defined l'abscisse keveling as the length of the trajectoire that a point makes as it moves along that curve we are studying. As we said, we use le repère Frenet when we're studying the movement of the point M that is moving along a curve. That's when we use the coordinate, or bien we use the repère Frenet. And when it's moving along a curve, or when it's forming a curve as it moves, that distance that it moves on that curve, we call it l'abscisse curviligne. And then I told you that at every point M that we have on that curve, we can associate in bars to it. We have the vector tangent T, which shows us the direction in which the point is moving. It's tangent at that point M on the curve. And then we also have the vector unitaire N, which is directed or oriented towards the concavity or in the inside of the curve. And then we have D, which is the binormal. It's perpendicular to both N and T. So as the point M advances on the curve, l'abscisse keveling changes. Okay, the length it's moving is changing. So let's say it moves 2 meters, then it continues moving 3 meters, 4 meters. You see that l'abscisse keveling is varying, and as it is moving on that curve, the tangent at each point is going to change. So you guys can picture that. Just imagine, for example, a circle. The tangent at every point on a circle is going to be changing. If we look at this figure that we have here, if the point M is here, you see the tangent is oriented in that direction. When the point gets somewhere here, the tangent will be oriented in that direction. So that's telling us that vector tangent varies as S is varying. So as S keeps on varying and changing the distance as it keeps increasing or decreasing, even the tangent is going to change suivant the changes in S de t. That's what this statement here that's been highlighted in orange is telling us. You can just try to imagine this as a point moves on the curve. The tangent at that point where that point M is going to be different from when it changes its position. It goes to another point on that curve. So we are going to begin with this expression here that we have dt over dt, d grand T over d petit t. We are going to try to break it down. And as usual in mechanics, we decompose expressions a lot to help us derive them. We look at the expression that we have for what we're deriving. We see what it has been expressed in terms of, and then we can decompose it so we can derive it properly and all that not. The goal is just to simplify your working, just to ensure you can advance and not stay blocked. Okay, so when we have dt over dt, we can decompose this. Okay, as we've been told, the tangent varies as the Labs equivalent varies also, meaning those two have a varying relationship with each other. So we can derive them with respect to each other. So we can break it down to have dt over ds multiplied by ds over dt. And we know that the s over the t, as we derived from the very definition of the velocity when we are finding the velocity, we said the s over the t is equal to the magnitude of the velocity, which we just called v without a flash on top. We just write v to show that this is the magnitude of the velocity. Vector vitesse or vector velocity has a flash on top of it, but the magnitude does not have a flash. So the s over the t, we said it's equal to v. And that's the v here. So now we have v multiplied by dt over the s. Now we are going to try and deal with this dt over the s. And there's a rule that we use normally when you're studying the movement of a point on a curve. For you to understand the movements properly on that curve, you try and divide that curve into circles, like you draw circles on the curve at different points on the curve, you draw circles. Why are you drawing circles on that curve? It's because circles are easy to study. Remember I told you right angle triangles are easy to study in trigonometry because we know the principles, we know the formulas to use. It's the same thing for circles. Circles are also relatively easier to study. It's easy for you to find expressions in circles. So if I am studying a certain point M, if I'm studying a certain point M here, I can draw a circle around this point M and make sure M is on the circumference of that circle. So I can draw a circle there. Okay, I'll draw a circle there with center C, So just imagine we've drawn a circle at this point, just so we can study the point M. So we can form a sector. You guys that did additional mathematics know what a sector is. For you guys that don't know what a sector is, I would like you to picture a pizza in your mind. Those things that you get, those the way they are divided, I know we call them triangles, but those are actually sectors. That shape, you have it coming like it's a triangle with a circular thing towards the end or an arc. We call that a sector, okay? So we form this sector from that circle, from the center to the circumference and from the center to another point in the circumference. And we call this part here the arc, I remember I talked about an arc yesterday. Yeah. And then we have an angle at the center there. We can call this angle d alpha. Now, in physics or in mathematics, whenever you see something expressed as d alpha or d alpha, it's infiniment petit. I talked about infiniment petit. It's very small. It's a small portion. So when we say d alpha, it means the angle there is very, very small. I can have an angle alpha, and then I can write d alpha just next to it, meaning I have just gotten a small portion of alpha, and that has become my d alpha. We usually use this d something to study something at a small scale, then we generalize it at a large scale. So if let's say I'm studying the surface of a sphere, and I know the surface is equal to S, I can first begin by just getting a small portion of it, and I'll call it the S. I will study that, and then I will now apply that on a large scale with the S. So I also have my small angle there, the alpha. This angle here is just to help me study this sector here, this small sector that we have gotten here. So I'll have my angle, the alpha, and I'll have my arc length there, and I'll have my radius. The radius is from the center to the circumference, bien sûr. Then we are going to now try and do some mathematics based off of this sector that we have formed on this curve. So we have dt, ds being equal to. Now we are going to decompose dt. We want to use this angle alpha, the alpha. So we'll say dt over ds is equal to dt over the alpha multiplied by the alpha over the s. We have just decomposed it the same way we have been decomposing. And then we are going to use a principle that I have already explained to you guys. And that's the dérivé of a vecteur unitaire par rapport à un angle. Okay, remember when we are doing the dérivé of euro par rapport à phi, we said it rotates 90 degrees and it becomes e phi. And when we also derived e phi par rapport à phi, we said again it rotates 90 degrees and becomes minus euro. We're going to use the same principle here. When we derive l'angle, the vector unitaire t par rapport à l'angle de alpha, it will also be rotating 90 degrees because we are deriving a vector unitaire par rapport à un angle. You have this concept, you have this principle in your notes. If you have gone through them, I'm sure you know about it. If you haven't, please go back to your notes, revise it, understand it well, and this is just going to be du gâteau. So when we derive a vector tangent par rapport à cet angle de alpha, we are going to get the vector n, which is 90 degrees to it. It's like we'll be making the vector tangent rotate 90 degrees. And when it rotates 90 degrees, it's going to come to this one, which is at 90 degrees to it, which is a vector unitaire n. So you see, we have dealt with this one. We have gotten an expression for it. dt over the alpha is equal to n. So now we continue solving. We are going to now deal with the alpha over the s. We see what is equal to the alpha over the s. So here they're telling us n vecteur unitaire qui se déduit de t par rotation de pi sur 2. What I'm from explaining to you guys. When you derive the vector tangent par rapport à un angle alpha, when we do dt over the alpha, it's like we're making t rotate 90 degrees. And when t rotates 90 degrees, it's going to go into n because n, t, and b, the three vector unitaire of the Repère Frenet are orthogonal. They are at 90 degrees to each other. That's why we have the t over the alpha being equal to n. Now we deal with the alpha over the s, and I told you that we are going to work with this sector. Those of you that did additional mathematics, I'm sure you enjoy this part because I'm sure you must have done this. For those of you that did not do it, I'll give you the formulas and you can try and research more based off of those formulas I'll give you. So they're telling us, en désignant par C le centre de courbure de la trajectoire au point M, I don't know what you can decide, sorry, centre du cercle auquel on peut assimiler la trajectoire au voisinage immédiat du point M et par RC égale CM, le rayon de courbure au point M, ONA. So from this, what that's supposed to get, there's some French that's maybe a bit complicated because it's new terms for you guys. Just know that C is the center of that circle I told you to form around, not around, but on the point M, okay? Making sure M is on the circumference of that circle. And C is the center of that circle. So if C is the center of that circle and the point M is on the circumference of the circle, that tells us that the distance CM is equal to the radius of the circle. And we shall call that radius RC. So they're telling us here, RC equal to CM. So RC is equal to CM, and CM is the radius, le rayon. Okay, perhaps that's a new word for some of you. When you see rayon from now on in mathematics and physics, it's radius. Le rayon d'un cercle or d'un cercle, it's the radius. So we have RC denoting the radius of this point. Now, I would like one of you to tell me, what was the formula for arc length that you learned? What's arc length equal to?
Theta R.
Theta R, where theta is the
angle.
The angle that the sector is forming also has. So this angle here. So we know that the arc length, the distance there is equal to the radius that we have RC multiplied by the angle which is in between. Now, we saw from the definition of Labsis-Kevelin that Labsis-Kevelin is equal to the distance that a point M moves on the curve. So if, let's say, initially my point M was there and then it moves to this position, we'll have this as our abscissa Kevelin. And as I told you, when we say d alpha, it means we have just gotten a very small portion of what we are studying. Okay, so since we have d alpha here, even our abscissa Kevelin, we will not denote it as S, but we'll denote it as ds because it's just a small portion of what we are studying. Infiniment petit. We study it on a small scale and then we bring it to a large scale and get our final results. So since we have the alpha here, even this, our arc length, which is in actual sense, the abscissa Kevelin, we shall call it ds. And since our friend has told us that arc length is equal to the radius multiplied by the angle formed by the sector, we will have ds, this arc length here, ds being equal to the radius, which is RC, multiplied by d alpha. And that's what we have here, that the guy actually circled. We have ds being equal to d alpha multiplied by RC. Then what we are trying to solve is d alpha ds. Don't lose track. We are trying to work out d alpha ds. So we have ds being equal to d alpha multiplied by RC. So here, if we just play around with our terms, we change the subject of the formula in trying to make d alpha over ds subject, we will divide d alpha by ds, and then we will bring the RC on the other side. It's going to become d alpha over ds is equal to 1 over RC. So we found the expression for this guy also, 1 over RC. RC being the radius, the distance from the center of the circle to the point M. So that's that. D alpha over ds is equal to 1 over RC. So we have worked out this guy here, this entire guy, dt over ds. We found dt, the alpha being equal to the vector unitaire n, and then we have found d alpha over ds being equal to 1 over the radius RC. So what's left to do? We can write the full expression here first as dt over ds, this one here that we're working out, being equal to vector vitesse v over RC, suivant n, vector vitesse v over RC, suivant n. Vector vitesse coming from this one here, the vector, no, sorry, not vector vitesse, but the module of the vitesse. Je m'excuse, please, I'm sorry about that. This is the module, so this v is the module from here, there, from there, that v, we write it there, over RC, that we got there, suivant vector unitaire n, that we got there. And we have our final expression of the acceleration being equal to dv over dt suivant t, dv over dt coming from here, this part here, dv over dt suivant t, it was this one, okay, dv over dt suivant t. So when you calculate your vector vitesse when you're doing vector vitesse, you just get its magnitude and you derive it by time, suivant t, and then plus v squared, the v squared, you have this v and you have this v multiplying each other, and you have v squared over RC suivant n. And that becomes your expression for the acceleration. And this becomes the acceleration tangentielle, and then this one becomes the acceleration normale. We denote them as gamma t, accélération tangentielle, because it's dans la direction de la tangente, and then we have this acceleration as the acceleration normal because it's in the direction of the normal. So this is your final expression for the acceleration in the coordonate Frenet. It's equal to dv over dt suivant t plus v carré divisé par le rayon du cercle RC suivant le vecteur unitaire n, as that there. and they're telling us accélération tangentielle, comme je vous l'ai déjà dit, commande les variations de la vitesse le long de C. Gamma n, accélération normale, commande les changements de direction de la vitesse. So this marks the end of the velocities and the accelerations. Okay, not the end. There's one more, but I'm giving it to you as an assignment for next week. Are there any questions on this?
Yes, I have a question.
Uh-huh.
Just that expression where it's the ds is equal to d alpha multiplied by RC. There where it is d alpha over ds. I don't know how that calculation came about, where it d alpha over ds is equal to 1 over RC.
Oh, we just divided. You see, you have the S is equal to d alpha multiplied by RC. So if I divide throughout by ds, I'll have 1 on this side. Then this side, I'll have d alpha multiplied by RC over ds. Then when I take the RC on the other side, I'll remain with d alpha over ds on one side being equal to 1 over RC.
Oh, all right. I would also
like just divide and separate.
Okay. I would also like you to just briefly repeat the last part. Yeah, after that equation.
Okay, so after this equation, we started from here. Okay, this term here, up here, we can leave it as it is. dv dt suivant t, that one is okay. Plus, now we're going to break this one down this side. V for dt sur dt. So we have this v here. Don't forget about it. This v, we have it there. We'll just get this part for now. dt over dt, which is this one here. So now dt over dt, we are going to decompose it into something that we can actually differentiate and get and advance from there. Because from here we're blocked. We can't go anywhere. dt over dt. We don't have an expression of the tangent in terms of time that we can derive and get a good answer from it. So we're going to decompose. We're going to say dt over ds multiplied by ds over dt. So now we have dt over ds multiplied by ds over dt. But we know that ds over dt is equal to le module de v, which is v. So we have this v here, the module de la vitesse, which is v, is equal to ds over dt. So this ds over dt, we're going to write it as v there, multiplied by this dt over ds. So we have this now. We have two v's, okay? We have two v's now. We have this v and that v. So we have v squared, and that's why we have a v squared here. We have a v squared. It's from this v that we've gotten here and this v that we had initially. Then we come to dt over ds. We are still going to decompose it because we cannot advance from dt over ds. We're going to decompose it into something that's going to allow us to advance. So dt over ds, we decompose it into dt over d alpha multiplied by the alpha over ds. And dt over the alpha is the derivative of a vector unitaire par rapport à un angle. And we looked at this, we said, when we derive a vector unitaire par rapport à un angle, it represents a rotation of that vector unitaire by 90 degrees, okay? And so when we make this tangent rotate 90 degrees, it's going to rotate into n. So it's like the derivative of dt over the alpha is going to be equal to n, just like we had the derivative of e rho par rapport à phi, it gave us e phi. It's like we rotated the e rho 90 degrees and it became sorry, e phi. So dt over the alpha, we've solved it as a n, the vector unitaire n. Now we are left with the alpha over the s, the alpha over the s. So that's where now we came to our sector, the sector that we have here, forming this arc length, this side that we are calling the S, as in Labsis Kevilin S, but just a small portion of the Labsis Kevilin. So we're calling it the S, and the angle it's forming there is the alpha, the large angle is alpha. You can have the large angle there, alpha, but because we're just taking a small portion of it to study, we are using the alpha. And the rayon of this sector, sorry, the rayon, the radius of the sector that's formed, Cm is equal to Rc, or denoting it by Rc. That's why it has R, but in the book we're using, or the PDF we're using, they denoted it as Rc. So we'll work with Rc. So Rc is the radius there. And I asked you guys, say, what's the formula for arc length, the arc length of a sector? And your friend said it's equal to the radius times the angle formed in between. For those of us that have never done sectors before and all that, that's the formula for the arc length. Arc length is equal to the radius of the sector multiplied by the angle that the sector is forming. So in this case, we'll have a ds, which is the arc length, ds, which is the arc length or the abscissa Kevilin, being equal to the radius, which is Rc, multiplied by the angle the sector is forming, which is the alpha. That's where this formula came from, the S being equal to the alpha multiplied by Rc. Then when you just play around with this formula, you just rearrange the terms in there so that you have the alpha over the S. You are going to have this. It's like, or you can just divide the alpha and the alpha. You have the S over the alpha being equal to Rc. Then you reciprocate everything. It's going to become the alpha over the S being equal to 1 over Rc. And that's where this has come from. And we are looking for the expression for the alpha over the S. We have found that the alpha over the S is actually just equal to the reciprocal of the radius, which is 1 over Rc. So we have worked out the T over the alpha, which is N, and we have worked out the alpha over the S, which is 1 over the radius. That's why we have 1 over Rc multiplied by N. Then we had this V here, which is the V on top. That's why it becomes V over Rc, suivant N. Then in the final expression, we have V squared, because I told you guys, we have this V here. We left it there for now, but now that we've worked out this entire expression, we can multiply it by this V also in our final expression. So we'll have V squared, and that's why it's become V squared over Rc suivant N. So we have our gamma being equal to dv over dt suivant t, and then we have worked out this. It has given us v squared over Rc suivant n. Is that clear?
Yes, it's clear.
Is it clear for everyone else?
Yes, it's clear.
Okay, lovely. So
Another question.
yes, David.
Yeah, just repeat on the vector unitaire, like what it means.
Vector unitaire. Vector unitaire is a vector whose magnitude is equal to 1. We call it vector unitaire. Tout simplement. It's just a vector whose magnitude is equal to 1. Is it clear?
All right.
Okay, good. So far, we have looked at the vitesse dans le coordonnées cartésien, vitesse dans le coordonnées cylindrique, vitesse dans le coordonnées sphérique. You guys are supposed to know that. And we have also looked at the vitesse dans le coordonnées or dans le repère Frenet. We have also gone on to study the acceleration dans le coordonnées cartésien, the acceleration dans le coordonnées cylindrique, l'accélération dans le coordonnées Frenet. What's left is the acceleration dans le coordonnées sphérique, okay? In some schools, you're not going to do that, but I'm sure in other schools, you're going to do that. In other schools like this school are in, yes, in the summer lessons, you guys are going to do it. L'accélération dans le coordonnées sphérique. I'm giving you guys that as your assignment due next week, Wednesday, before our class, okay? Now, it's a bit complicated. It's very long. It's a very long expression, and I'm sure you guys are going to make so many mistakes because you are novices in this field. So what I'm going to do is I'm going to send you the answer, the final answer for the acceleration down the coordinate spheric. I'm going to post it in the group right now. So, and what you're going to do is you guys are going to have to reproduce that final answer I'm going to send you guys, showing your working. And you will be working in the same groups of 3 that you formed. So if you disobeyed my orders yesterday when I told you guys to form 3 groups and send me your assignment, form it now or form them after the class and do this assignment. You are going to calculate the accélération dans le coordonnées sphérique. I will send you the final answer and you guys are going to have to reproduce that answer, showing your working. I just want to see if you guys have understood how to derive these expressions, how to move from vitesse to acceleration, et tout ça, how to do with the rhos, the R's, the ER, E theta, theta, phi. If you know how to play around with these things and simplify them, I want to see that. So it's due next week. You are supposed to do it. Calculate l'accélération dans le coordonnées sphérique. So you will get the vitesse dans le coordonnées sphérique, which we did yesterday, and you will derive that, and you are supposed to land at the acceleration. So what's next is this one. In the polycopy, what's next is this example de mouvement. I'm not going to do this with you guys because they are not so interesting in your working for mechanics. You're not really going to get questions on this, but it's important that you know them. They are easy to understand, so you just revise them on your own. We won't do them here together, but you guys can do them on your own. Just go through the stuff. Just go through it. You'll understand when you go through it. It's direct. I'm just telling you examples of movement, so you just have to imagine a bit. Yeah, the same stuff we're doing, just continue with your imaginations. We will jump direct to this last part here, changement de référentiel. So at this point, we're going to take a break, 5 minutes break. You guys can drink some water and do what you have to do. We are going to come back at 12:55. At 12:55, we are going to continue with our lesson. So pause 5 minutes, rest a bit, try to understand what I'm from explaining to you if you didn't understand, and we'll come back after 5 minutes. Okay, welcome back, guys. Welcome back. We are going to continue. So the last part we're doing is la partie 11, part 11, changement de référentiel. So up to this point, we have been doing calculations in one referentiel. When we study le vecteur position, we just said dans le référentiel R, soit un référentiel quelconque R. We're just dealing with one referential. Now, I want you guys to get that idea behind you from now on, because you'll not be dealing with one referential, you'll be dealing with more than one, perhaps two or three or four sometimes, okay? You'll be dealing with one referential in movement with respect to another referential. So you have to take into consideration the fact that you have two referentials there and one moving with respect to another, with one of them fixed and the other one mobile. One is moving. So there are certain calculations that are going to change. There are certain things that we're going to introduce in. We began with one referential just so you can understand the concept of velocity, of acceleration, vector position, et tout ça. But in reality, it's not that simple. It's a bit more complex, okay? Because we have, you might be in a laboratory, for example, or maybe I might be using the sun as a fixed referential, okay? And I'm studying the movement of something on Earth, and I'm using the Earth as another referential. So first of all, the Earth is moving with respect to the sun, and then that point I'm studying on the Earth is also moving with respect to the Earth. So if I'm using the sun as my fixed referential or as my absolute referential, I cannot just go directly the differentiating and doing that and that. I have to take note of the fact that one referential is moving with respect to another, then proceed with my calculations. So what they're telling us in the introduction here is that's what I'm from explaining to you guys, is that jusqu'à présent, on a supposé que le mouvement du point matériel était décrit par rapport à un référentiel fixe. En effet, on peut définir un mouvement par rapport à un référentiel quelconque, lui-même au mouvement quelconque par rapport à un autre référentiel. It's like you can define the movement of a point par rapport à au référentiel R', and you're being told that R' is moving with respect to R. So it's like you have two referentials there, and as I've told you, you need to do certain things, you need to introduce certain things to just take note of that movement between the two referentials. And then it goes on to say, le problème posé est le suivant. R et R' étant deux référentiels en mouvement quelconque, l'un par rapport à l'autre. Quelle relation existe-t-il entre les caractéristiques cinématiques, vitesse et accélération d'un même point relatif à R et R'? So now this is what we are going to work out. We are going to try and find these expressions that exist between that exist in a point that is involved in this more complex movement of one repère moving, or one referential moving with respect to another referential. So we'll be studying the cinematics behind that. We'll try and find the velocities, the accelerations of that. And from now on, when we tell you to derive something, we will be telling you in what referential you are deriving it in. And you also need to consider what referential that expression you're deriving has been written in. So if you're deriving with respect to one referential and your expression has been written in another referential, there are certain things that you will have to bring in that we are now going to look at in this part, changement de référentiel. So, l'introduction du repère R' est choisie de telle façon à ce que le mouvement du point matériel il soit plus simple à étudier. On appelle par commodité de langage, first of all, R, we're using R as the referential absolu qui est fixe. So you first of all have one repère which is fixed, and that's your absolute referentiel. We'll call it referentiel absolu. Then we also have un référentiel R' qui s'appelle référentiel relatif. which is mobile, which is moving with respect to R. So as I told you, you can have the sun as your referential absolute, which is fixed, and you have the earth moving around the sun. Yeah, so that referential, the earth, is in movement with respect to the sun. And then you can go on to study the movement of the point on the earth. So it's like you'll be studying that movement of that point with respect to two referentials now. One which is moving with respect to another, and another one which is fixed, and that is the sun. So now, 11.1 goes on to give us the dérivée d'un vecteur par rapport au temps relative à R et R1. So let's see how it goes. So they're telling us, considérons deux référentiels, R, O, I, J, K. So we have the first referential, origin O, avec la base IJK. Then we have our second referentiel, R1, centre O1, or the origin is O1, avec la base EX, EY, et EZ, et un vecteur U. So we have a vector U. It's like this is the vector whose movement we are studying. So now they tell us that the expression for U in R, okay, when we write it in R using the base for the referential R is going to be XI plus YJ plus ZK. This is down R. And then we can also write the same vector U, but this time not in R, but in R1. So the base we're going to use this time is going to change. We're going to have X1 suivant EX plus Y1 suivant EY plus Z1 suivant EZ, because we have changed the referential and the base has changed. Last in the referential R, we had the base EJK directing us in terms of directions to go in. But in the referential R1, this time we are using the base EX, EY, EZ to direct us in which directions to go in, because it's a different referential. Yes, you can have more than two. You can even have 5 referentials. When you go to faculty, okay, maybe even here with me, we'll be solving some questions. They'll have 3 referentials, so you need to know how to work around them. We're going to see that. We'll see that. Ne vous inquiétez pas. So, RP en mouvement quelconque. So these are referential. They are moving anyhow. Yeah, mouvement quelconque. So they're saying d de U dt dans R. Now this is a normal differentiation, because we have the expression for U in R. So it's like U belongs to that expression. U belongs to that referential R in that case. So even when we're deriving it, we're going to derive it directly. It's just going to be X point I plus Y point J plus Z point K. The same thing for this one here when we derive U dt par rapport à R1, because we have the expression for U written in the referential R1 or écrit dans R1, we have this expression. So we can just derive this expression directly without having to worry about anything, because we have the expression dans R1. So even as we are deriving par rapport à R1, we just go directly without worrying. It's going to be X1 point, Y1 point plus Z1 point. So they're telling us à partir de R1 égale this, exprimons. Now, this is where it gets a bit more complicated, a bit more complex. We are deriving U. When we say U and the slash R1, it's like U written in R1. So we are using this expression here, written in R1. So when you see something written like this, U, a slash, a small slash, and then R1, what do you call these things? Superposition, subposition. I've forgotten what you call it exactly, but it's written just under it here. Forgotten exactly what you call it. Yeah, it's just written under there. It means they're telling you the vector U écrit dans R1. So here we have 2 expressions, one written in R, the other one written in R1. So when they write it like this, they're telling you get the one written in R1. So it's the one we're using. But why am I saying it's going to be a bit more complicated? It's because we will be deriving in another repère, or par rapport à un autre repère. So it's like I'm telling you to get an expression written with the coordinates on Earth, but we are deriving it with respect to the repère sun. So we have to do something. Another example I can give you to understand this, for example, is trying to get a residency card here in Morocco. The things Moroccans have to do before getting their residency card are different from the things we foreigners have to do for us to get our residency card. Because Moroccans belong to Morocco, this is their country. This is like their referential. They belong to this referential. They have been written in that, their expression has been written in that referential, Morocco, they are light skin and they are Arab. So for them, it's just going to be direct. They'll just go there, present their birth certificate, and they get their residency card. But for us foreigners, me, Charles, my expression has been written in the Zambian referential. So if I want to get a residency card here in Morocco, I will have to do something more than a Moroccan because I do not belong to this referential called Morocco or this country called Morocco. I belong to another referential, Morocco. So it's like I'm foreign in this referential. So there's some extra work I need to do to cater for that fact that I am foreign. It's the same thing here. We are deriving U, written in a referential R1, but we're deriving it in the referential R. So it's like we are deriving it in a foreign referential. So we cannot just go directly the way we were deriving before this. We will need to introduce certain things to cater for the fact that U, the expression for U that we are using has not been written in that referential we are deriving it in, okay? So it's going to appear something like this. D de U écrit dans R1 dt, and you're deriving it par rapport à R is equal to, you're going to derive it normally first of all in R1, we'll see the general formula. Just you treat it as though you're deriving it in R1 first of all. Then you do certain things, these are the things that you do. This side, you derive the EX par rapport à dt dans R. You also derive the EY par rapport à dt en R. You also derive the EZ par rapport à dt en R. And then we introduce another new symbol or term, which is the omega. Omega represents rotation or la vitesse angulaire. Okay, it's like vitesse angulaire. It's like when something is rotating, it's going around a circle, so to say. The rate at which the angles are changing, because when it's going around the circle, the angle from where it started from is changing. So the rate of change of that angle with respect to time, that's the vitesse angulaire. It's like the speed at which the angles are changing as it's rotating, as it's going around, as it's rotating.
I have a question.
Uh-huh.
What is the meaning of that color in which I'm seeing? Which you are using? The one which is more like a modulus, but it's not complete on both sides.
Ah, this one.
Yes.
This one is showing you that you are deriving it par rapport à R, or you're deriving it in R. Okay. You write a line, then they put an arrow this side. It's telling you that you are deriving it in this referential. That's why I'm telling you that from now on, when we give you a vector or an expression to derive, you have to look at the referential it has been written in, and then you have to look at the referential we are asking you to derive it in. If it has been written in the same referential we are asking you to derive it in, you will just go direct with a derivation that you know. But if it has been written in a referential that's different from the referential we are asking you to derive it in, there's a certain formula we are getting to it that you are now going to have to use, okay, to derive that, because you are deriving a foreign expression in that referential. That's why I gave you an example of me trying to get a residency card in Morocco. I won't do the same things as a Moroccan trying to get a residency card here, because that Moroccan belongs here. I don't belong here. I am a foreigner here. So I have to do some extra work, some special work, special only to foreigners. So it's the same here. That expression, if it's written in a different referential than we are deriving it in, it's foreign in that referential we are deriving it in. So we need to do certain special things, certain special treatments, certain extra treatments to ensure that we derive it in that referential, that foreign referential it is in. Okay, it's like I have an expression xe plus yg plus zk, and I tell you to derive it in cylindric, for example. The rules that apply in the cylindric are different from the rules that apply in the Cartesian, so I can't just go on directly. I have to take note of the fact that that Cartesian there, it's foreign in the cylindric, so I have to do certain things to ensure that I get the correct answer. I cannot just go directly about it. So, Ruben, this line here is telling us which referential we are deriving it in. So when you see this line, and then you look to the right of this line, the letter that you see there is going to be the referential you are supposed to derive that expression in.
Okay.
So, yeah.
Thank
So they're telling us, on sait que la dérivée de Ex dt égale à ça, la vitesse angulaire de R1 par rapport à R. So it's like R1 is rotating with respect to R, it's rotating around R, so to say, and that's the vitesse angulaire there. We read it as omega vectoriel Ex. Now, I tried to look up this. I unfortunately couldn't find it because here what they've said is on sait que. We know that. Personally, I didn't know that. And I'm sure you guys also don't know that. So for now, you can just take it as it is. I'm sure they've proven it somewhere that d de Ex dt dans R is going to give you that. Okay, can give you this, the vitesse angulaire vectorielle Ex. But all this is just going to the formula that we'll be using. So this is not so important, but it's mostly because I don't understand it myself. But if there's among us two people that have certain particular interest in mechanics, you can try and look into it and try and explain why this is so. That's how you learn. So now they're telling us, il vient donc d de U écrit dans R1 dt par rapport à R égale. It's like you're deriving this expression of U written in R1. You're deriving it in R or par rapport à R, le référentiel R is going to be equal to, you are first going to derive it in that same referential it's been written in directly, okay? So if I get an expression U written in R1 and they're asking me to derive it in R, what I'm first going to do is I'm going to derive it in R1, okay? You see this written in R1, derived in R1, just directly like that, plus, then I will do some calculation here. I'll get the vitesse angulaire, which will be given, by the way, vitesse angulaire de R1 par rapport à R. This is to show that I have R1 in movement with respect to R. Okay, so I'll get la vitesse angulaire de R1 par rapport à R, then vectoriel, the same vector I'm deriving. This one is just U. Okay, this one is just U, X1 EX plus Y1 EY plus Z1 EZ. It's just U written in R1. So I'll get the vitesse angulaire vectoriel, the same vector I am deriving, where this formula is born. This is from where this formula is born. Formule de Bohr. You guys have to know it. You know it. This formula is going to destroy you if you don't know it. You're going to make mistakes. Yeah, so you guys will do Mécanique du point, you graduate into Mécanique des solides. You will be working with Formule de Bohr through and through, because you will be working with more than one referential. Okay, you're not going to be working with one referential. You would be lucky to work with one referential. Mostly you are working with two referentials. And if you're working with two referentials or more, you are going to need to use Formule de Bohr, because you will be deriving expressions written in one referential in another referential. So the formula, the general formula becomes d de U écrit dans R1. So U written in R1, its expression has been written in the referential R1. You're deriving it par rapport au temps, but you're deriving it par rapport à R, or you're deriving it in the referential R. Even though it's been written in R1, you are deriving it in a foreign referential, which is R. So the formula is going to be, you will first derive it in its own referential. So if it's been written in R1, that's its referential, you will first derive it in that same referential R1 in which it's been written. Then you will add this one here to show you that, okay, this term here to show you that, okay, this referential, this expression has been written in, is in movement with respect to this other fixed referential. So you have vitesse angulaire R1, vitesse angulaire de R1 par rapport à R. This is showing that R1 is rotating or is in movement with respect to R. Vectoriel, the vector that you are deriving this side. So this is how you just remember it. So if you have dv, this side you have v. If you have OM here where there's U, this side you have OM. If you have what? This side, it's just the vector that you are deriving that you put this side. Vitesse angulaire, vectoriel, the vector you are deriving. Vitesse angulaire, vectoriel, the vector you are deriving. So I repeat, formula the ball. You are deriving a vector written in one expression, but you are deriving it in written in one referential, but you are deriving it in another referential. You are deriving a vector written in one referential, but being derived in another referential. So it's like you're deriving it in a foreign referential. So what you first do is you will derive it directly in its own referential, then you include, remember I told you there's a certain special treatment you are supposed to do to show that, okay, it's in a foreign referential that I'm deriving this. So this second term, this side in formula de Boer, is what we are using to show that I am deriving it in a foreign referential. It is this one, the vitesse angulaire, which is omega, the R1 par rapport à R, showing you that RA is in movement with respect to R vectorial, the vector you are deriving. Is that clear?
It's clear.
Okay, great. So there's just a few remarks here. Remark number one. Un repère R' est en mouvement de translation par rapport à R si A et B deux points fixes quelconques ou deux points quelconques fixes de R1. Le vecteur AB reste constant au cours du temps. So if it's just being translated, it's like the direction of A and B. Or yeah, 2 points, you have 2 points A and B in a certain referential. So if that referential is just being translated with respect to another referential, it's like the direction of A and B, or the value of A and B will not change. Okay, I'm sure you guys know what translation is. Translation is just moving one point to another. It's different from rotation. Rotation is like going around something, but translation is just moving from one point to another. I think it's, I don't know if I should say rectilinear. Okay, not really rectilinear, but it's just different from rotation. Rotation is going around something. Translation is just displacing yourself from one point to another. Can be in a straight line, can be in a bent line, but as long as you've just moved from a certain point to another. So when you translate, you are not changing the direction of any point really. When you are turning, you're changing the directions of things in that object you are turning constantly. But when you're translating, the points remain fixed just the way they are. Then the second remark is saying, on dit que le repère R1 effectue un mouvement de rotation par rapport au repère R autour d'un axe delta si tous les points du repère R1 situés sur delta sont fixes par rapport au repère R. If you are rotating around something, that thing you're rotating around is not rotating itself. So that thing you're rotating around is going to be fixed. Its points are going to be fixed. So if you have a repère R1 rotating around a certain axis, which we call delta, and that delta belongs to R, the points on that axis that R1 is rotating around are not going to change. They're going to remain fixed because they are not moving. It's just what's rotating around it that's moving. So that's what they're trying to explain here. The points on that axis around which we are rotating are going to be fixed. Then they're telling us, lorsque R1 est en mouvement de translation uniquement par rapport à R, we have vitesse angulaire being equal to 0. I'm sure this is obvious because I told you vitesse angulaire is like the speed at which the angle is changing when a point or an object is rotating. So if there's no rotation, it means there's no angle changing because it's not rotating. So if the vitesse angulaire, so if the point is just being translated and not being rotated, if it's only being translated, it's saying en mouvement de translation uniquement, okay? So meaning there's no rotation because it's just uniquely translation, meaning the vitesse angulaire is going to be equal to 0 because there's no rotation. And you are going to have d de u R1 dt dont R being equal to just this term here, just deriving it in its own referential without that expression containing the vitesse angulaire because the vitesse angulaire is equal to 0, like from this expression here. Because the vitesse angulaire is going to be equal to 0, this entire term this side is going to be 0. So we'll just be left with this. And we'll have this being equal to that there. If it's translation uniquement, only, that's when the vitesse angular is going to be 0. But as long as there's rotation, the vitesse angular is going to be different from 0. And then, dans le cas où U est fixe dans R1, so if U is fixed dans R1, we cannot derive it in R1 because it's fixed in that referential. So it's going to be equal to 0. So this term there is going to be 0, and we'll just be left with this term. So we'll have d de U écrit dans R1, de T dans R being just equal to this term this side, because this first term is 0 because U is fixed in R1. It's not changing, it's not moving. So when we derive it in R1, it's going to be equal to 0 because it's constant in R1. Then we have the derivé of the vitesse angulaire de R1 par rapport à R par rapport à T, donc R being equal to the vitesse angulaire de R1 par rapport à R, the dérivé par rapport au temps dans R1. And they're telling us the vector vitesse angulaire ou le vecteur oméga admet la même dérivée par rapport au temps dans R et R1. So these two are equal. Whether you derive la vitesse angulaire dans R1 or dans R, it's going to be the same thing. Okay, it doesn't depend on the referential you're in. So even if you have it written in one referential and you're trying to derive it par rapport à un autre referential, the answer is still going to be the same. It's not going to change. It doesn't depend on that unless these other terms, these other vectors. But the vitesse angulaire is a special case. It's just going to be the same thing. So take a look at this formula, formula de Bohr. Understand it very well. Keep it in your mind. Look at it. I hope you guys are looking at it. Read it through. D de U écrit dans R1, dt dans R égale, you derive it in its own referential, not its foreign referential, because here they're asking us to derive it in a foreign referential. So we will derive it first in its home referential or its own referential, and then we are going to include this term to show that we are deriving it in a foreign referential. So we'll say omega de R1 par rapport à R vectoriel, the same angle we are deriving. So now that you guys have looked at it, that's the formula we are going to use from now on. Okay, it's a formula we are going to use from now on to calculate the vitesse and the acceleration when we are working with different referentials. So, composition de vitesse. We are almost done. Composition de vitesse. On considère deux référentiels R, O, X, Y, Z, repère absolu. The one that's fixed, we call it un repère absolu. Le mouvement de M dans R est dit mouvement absolu. It's like the entire movement. So if you're studying two referentials, one in movement with respect to another, that one that's fixed. When you study that point M with respect to that referential that's fixed, you'll be studying the entire movement, as I will show you in a bit. I'll try to demonstrate on a piece of paper. Then we also have R prime, which has origin O prime, and X prime, Y prime, Z prime, repère relative au mouvement par rapport à R. Le mouvement de M dans R prime est dit mouvement relative. It's like it's just moving in that small repère. And that's why we call the movement par rapport à la référentielle absolue. We call it the absolute movement because you are now studying the entire movement of the point M. I know it's a bit vague for now. I'll try to demonstrate so that you guys get the clearest picture. Then we have also le mouvement de, this last point, get it in mind. Le mouvement de R' par rapport à R est appelé mouvement d'entraînement. So if we have two referentials, one moving with respect to another. When we study the movement of that référentiel with respect to that other référentiel, we call that le mouvement d'entraînement. So from now on, whenever you see d'entraînement, just know it's telling you how one référentiel is moving with respect to another, okay? That's d'entraînement. So we are going to find vitesse d'entraînement, accélération d'entraînement. So when we say vitesse d'entraînement, it's the vitesse of that référentiel par rapport à un autre référentiel. And when we say accélération d'entraînement, it's like the acceleration of one référentiel with respect to another référentiel. So I want you guys to do what we did last time. I'll stop the sharing for now. I want to go to the participants, go on Charles and Kalandula and pin my video as I try to demonstrate to you guys what we are talking about when we have two referentials. You guys can see what I'm projecting on the screen, huh?
Oui.
Okay, okay. So we have with us here, we have this repère, okay? We have this, okay, actually I'll just begin from the top. I have one repère, R, O, X, Y, Z. I have another one, R prime, O prime, X prime, Y prime, and Z prime, okay? So this one, the first one is my absolute, it's the one that's fixed. The second one is the one that's in movement with respect to the first one. And it's something like this, it goes something like this. So I have my repère, this one, the absolute one, with origin O, and with the x-axis, the y-axis, and the z-axis. Then I have this other smaller one, not that it's always smaller, yeah, but it's us here. It's center O prime with the coordinates x prime, y prime, and z prime. Okay, so what we're being told is this repère is moving with respect to this big repère, and also we have this point M. Okay, so now they've told you, for example, to find the vitesse, we say vitesse de M dans R. Okay, they've told us to find this. I've written here, vitesse de M dans R. It means we will be finding the vitesse, how fast M is moving in the referential R. Okay, we're looking at how fast it's moving in the referential R. But if you look at this, M here belongs in this referential R prime. Okay, I can even write maybe the expression for OM. I can write the expression for OM in R prime as, for example, X prime, maybe EX plus Y prime, Y plus Z prime Z. I have that. I have my OM written as that. It's been written in R prime, okay? I have my OM written in R prime. That means OM belongs to this referential R prime. But they want me to find the vitesse of M par rapport à cette référentiel, the big one. So how am I going to do it? I'm going to decompose my movement. I will first study the movement of M in this repère, this small repère to which it belongs, and then I am going to study the movement of this repère R prime with respect to this big one now, you see. So in the end, I will have studied the movement of M with respect to this big repère. It's like I would have done M with respect to that. And then when I study the movement of this to that, it's like I'm getting the entire movement of M with respect to this point. So it's like I break it down from there to there, I study it, and then from there to there. And that gives me the absolute movement, okay? So we're being told that this referential, sorry, not point, but this referential M is moving with respect to this one. So it can be, there's two types of movement. Sorry, I didn't mention this before. There's two types of movement. We have translation and we have rotation. So when they tell us that the referentiel est en mouvement par rapport à un autre referentiel, it can be translated and it can also be in rotation. So if it's translated, you have it moving like this, like that, like this, like that, going forward, comes back. It's just being translated like that. And if it's rotating, you have it going round this referential, round it like that, round it like that. Okay, so you need to take all that into consideration. So we are trying to study vitesse de m dans R. So we have vitesse de m dans R. I can write it like that. It's going to be equal to, as we said, vitesse is the derivative of the vector of position. So I'll have d de OM dt dans R, because I'm studying it dans R. So I'll have that expression d de OM dt dans R. Then, as I told you, from now on, when we give you an expression, look in what referential or in what repère it's been written in. And then when you see which repère has been written in, look at the repère we are asking you to derive it in. If they are different, you will need to use formule de bord when doing it. So in this case, we have this expression OM has been written in this referential here, or in this repère, R prime, and we're being asked to derive it in R. It's different. We are being asked to derive it in a foreign referential. So we need to use formule de bord in this case. But before we get to that, we are getting way ahead of ourselves. They're asking us to study the movement of the point M in R. So if it's the point M in R, we'll be starting from the origin of R there at O, going to M. So it's like we'll be moving like this, like that. Sure, give me a sec. We'll be moving like this. We'll be moving from O to there, and then from there to there. And that's how we're going to study our movement. That will mean OM will be equal to O prime, first of all, O prime plus O prime M. Okay, it's going to move from O to O prime, and then from O prime to M, because we're being asked to study the movement of M dans R. So if it's dans R, we are going to start from the origin of R to M. But if we had been asked to study the movement of M dans R prime, if it was in R prime, we would have just started from the origin of R prime to M, and that's it. But because we're being asked to study the movement of M dans R, we'll start from here all the way up to there. Okay, but it's going to be a bit complicated, and we don't have the expression for OM directly from there to there. So we'll decompose it from O to O prime, and then from O prime to M. Okay, so we'll have O M being equal to O prime plus O prime M. And that's on this, we'll build our calculation for the vitesse on this same term. OM being equal to O prime plus O prime M. Simply from here, we'll just decompose it from here, from there to there, from origin to origin, then from the origin of the referential relative to this one. So this was just to show you what you have to have in mind a bit when we're telling you we are studying le point M écrit dans un référentiel qui est en mouvement dans un autre référentiel. It's like you have this point M in this referential, and this referential itself is moving with respect to this big referential, and the movement can be a translation, meaning the referential will be going like that, and like that, like that, and like that. It's being translated, or it can be rotating. So when it's rotating, it will be moving like this, going around the referential, or I don't know in what direction will be rotating, depending on l'axe de revolution, l'axe de rotation. Whether it's going around the z-axis, or it's going around the y-axis, or it's going around the x-axis. But I'm sure you guys get the picture. It's going to be rotating. So it can either be translating like that, or it's moving like that. So if you are studying the movement of the point M in this referential, the big one, you will first have to take into consideration the movement of this referential, the small one that M has been written in, or in which M belongs to, the movements it's making with respect to this one. And then now we're going to look at the movement M is making with respect to this. It's like you are in space, and you want to study the movement of your friend running, for example. They are running. So you are seeing it in space, from a distance. You are out of Earth, you're seeing it in space. The Earth is moving around the sun, not so. The earth revolves around the sun. So it's like the distance is changing there. And your friend on earth is also running. So when you are studying the movements of your friend on earth, you as the observer in space, you will need to take into consideration that movement that the earth is making, because it's going to be changing the distance of your friend. Because if you just go directly into studying the distance of the distance your friend has moved, the earth has also moved a certain distance. So the distance that your friend has moved is going to seem like it's a greater distance than it was before. It's the same thing as when you're walking on a bus. A bus is moving and you're walking on that bus. Maybe you just move 2 steps, you move like 2 meters. Because the bus is moving, a person observing you outside is going to think you would have moved more than 2 meters, because the bus would have covered a certain distance itself. So it would have made you seem as though you would have moved a greater distance than the 2 meters you moved on the bus. So it's like a person observing you from the bus will only see you move 2 meters, but the person observing you outside the bus will see you move a greater distance because the bus itself is moving. Okay, it's the same thing here. When you are in this referential, the referential R prime, and you're trying to study the movement of M, you only take into consideration this movement of M because you are in the same referential with it. But if I tell you to study the movement of M par rapport à cette referential R, you need to take into consideration the movement of this the movement of this referential R prime, because its movement is also affecting the movement of M, because M is moving with it. Just as in the example of when you are moving on a bus and someone is observing you outside the bus, or when you're moving on earth and someone is observing you out of the earth, because the earth or the bus in that instance is making its own movement, it's going to seem as though you are moving more than you are actually moving, because that distance that the bus moves is going to make the distance you've moved seem greater. I don't know if you guys get the concept there.
Yes, we do.
Okay, so that's why we are going to, first of all, study the movement of this referential with respect to this greater referential, and then we are going to study the movement of the point M with respect to this referential, now the referential to which it belongs. So we can go back to the...
Oh, before that, I've got a question.
Yes?
Yeah, is it possible that you can solve the movement of OM just from one diagram without combining the two?
It depends on which referential you've been told to study the movement of OM or the movement of M in. If you are studying it in R and OM belongs, and the point M belongs to R prime, you will need to take into consideration both diagrams. But if you're being told to study the movement of the point M and the point, you're being told to study the movement of the point M and it belongs to R prime, and you're being told to study its movement in R prime, there will be no need to use both diagrams. You just study it in R prime. You have to compose the movement when you're being told to study something that belongs to one referential or something that's written in one referential, and you're being asked to study it in another referential. You get the difference there.
Yes, I get it.
Okay, good. So, as we can see here, OM is equal to O prime, as I'm from showing you guys, plus O prime M. That's OM. It's now, we have decomposed it to help us study the movement properly, okay? Because when we say O prime, it's like this O prime will help us to study the translation of that referential with respect to the other referential, and this O prime M now is going to give us the movement of the point M with respect to that referential in which it belongs to, with the center O prime, as we saw from the diagram. So they're saying OM vector position dans R. So when we are in R, R has origin O. So that means if we're in R and we're studying the point M, our vector position is going to be OM. But when we are in R prime has center O prime. That means the vector position will be O prime M. So if we're studying it in R prime, we'll just be starting from O prime up to M. But if we're studying it in R, we'll be going all the way from O, the origin of R, up to M. So it's going to be, you guys, please take note of these things. Know them well, because some questions they'll be asking you to study, for example, in R prime, and you will make the mistake of using OM instead of using O prime M. And sometimes they don't use O. Sometimes they'll tell you the origin of the referential R prime is M prime. So when they tell you to study, no, study the thesis of the point M in R prime, you will need to use M prime M as your vector position. Okay, that's what you'll be using. When we tell you to say study a point M in a certain referential, get the origin of that referential. So if we're studying it in R prime, get the origin of the referential R prime, which is going to be O prime, and your vector of position is going to be O prime M. If we're studying the movement of M in the referential R, you will use the origin of R as O, and your vector position will now be O M. So get the difference, try to understand these things. These are the things that cost people marks, okay? You have to know the origin of what referential and in what referential you are studying that point in. So when we have this expression now, all you have to do is to derive it for us to get the vector vitesse, because we know vector vitesse, c'est tout simplement la dérivée de la vecteur position. So we'll have 2 de OM dt. We're deriving it in R. Okay, we're studying the movement, the absolute movement. And because R is a fixed repère, for us to get the absolute movement, we will be studying it in R. So we're deriving OM in R. So it's going to be equal to the derivative of OO prime dt still in R plus the derivative of O prime M dt in R. Okay, so this one, OO prime belongs to R, okay? OO prime belongs to R. If you remember the way the diagram was looking, OO prime is in R, it's not in R prime, it's in R. So this one will derive it directly without doing anything to it. But when you come to O prime M is in R prime, okay? O prime M, c'est le vecteur opposition dans R prime. So O prime M belongs to R prime, and we're being asked to derive it in R. So here now we'll need to use formule de Bohr. This is what I told you. When we give you a vector to derive, ask yourself, in what expression, in what referential has its expression been written? You tell yourself, oh, O prime M has been written in R prime, or O prime M belongs to R prime. Oh, so it's been written in R prime, or it belongs to R prime, and I'm being asked to derive it in what? Oh, I'm being asked to derive it in R. So I'm being asked to derive it in a foreign referential. Aha, okay. So here I'm going to use formule de Bohr because I have two different referentials in play. So we are going to go to formule de Bohr. So when we're deriving 2 de O prime M dt in R, it's going to be 2 de O prime M dt in R prime. As I told you, when you're using formula de Bohr, you first derive it in its home or its own referential. So since O prime M belongs to the referential R prime, when we use formula de Bohr, we will first derive it in the referential it belongs in, which is R prime, and then we will add this extra term to show us that, oh, we were deriving it in a foreign, or we are deriving it in a foreign referential. So we'll introduce the angular vitesse, or omega. So we'll say omega de R prime par rapport à R vectoriel, that vector which we are deriving. So the vector we're deriving is O prime M. So it's going to be vectoriel O prime M. So when we get this, we are going to write it now. We'll get this and we'll bring it there, we'll substitute it there. So we're going to have 2 de OM dt dans R égale 2 de O prime dt dans R plus 2 de O prime M dt dans R prime. This one here plus oméga de R prime par rapport à R vectoriel O prime M. Okay, and this is going to be your vitesse, your new vitesse, when you have un changement de référentiel, because you have a changement de référentiel here. So when you have a changement de référentiel, this will be your new expression for the vitesse. And we have notations here. We have, first of all, this first part here, d de OM dt, dont R is the absolute movement, the absolute vitesse. We denote it as la vitesse du point M dont R. As I told you, Ruben asked, when we have a line here and we have an arrow there, what does that represent? They are telling you in which referential you are working in which referential you are deriving it in, you are studying it in. So either you write it this way or you can write it this way. You write M/R. So we say vitesse du point M dans le référentiel R. Then we have this d de O prime. It's just going to be how the point O prime is moving in space, its translation. Okay, so it's going to be vitesse de O prime dans R still. And then we get this d de O prime M dt. Well, this one was studying it in R prime. That's why here we'll have vitesse du point M dans R prime. Okay, dans R prime, because here we are studying it in R prime. Why is it in R prime? Because in Formula de Bohr, we are obliged to study it in its own referential first, then we do the product vectorial of omega and the vector we are studying. Then these guys have names. Oh, so you have the final formula as that there. We have vitesse absolue. We call this the vitesse absolue, vitesse du point M dans R. We call it vitesse absolue, the absolute movement, like everything now, everything taken into consideration, the movement of one referential with respect to another, the movement of the point M with respect to one referential. We add all that and we get the total movement, and we call it the vitesse absolue du point M par rapport au repère absolu R. Then we have vitesse du point M par rapport à R prime. We call this vitesse relative because it's not complete. It's just the vitesse of the point M with respect to one referential. Okay, it's just with respect to the referential R prime. Okay, and that R prime is moving. So we cannot take that as our vitesse because there's more happening to the point M that we have to take into consideration. That's why I gave you the example of someone walking on the bus and someone observing from outside. If for the person observing outside, just seeing the person walking on the bus 2 steps, and that 2 steps is equal to, for example, 2 meters, the person cannot take that as the absolute vitesse. It's just relative to the bus. But if you want to get the entire movement of that point, the entire displacement, you also need to include the distance that the bus moved during that time that the person was moving. So if you just take into consideration the movement of the person alone, just walking on the bus, the 2 steps, the 2 meters, that's just going to be the vitesse relative to the person being on the bus. But if you want the absolute movement, the entire movement, you also need to put into consideration the movement of the bus. And in this case, the movement of the bus, we'll call it the vitesse d'entraînement. As I told you before, d'entraînement, whenever you see the word d'entraînement, just know they are telling you to study the movement of one referential to another. So we have first the vitesse de O prime dans R. Vitesse de O prime dans R. This one is telling us how the translation of the referential R prime was with respect to the referential R. And then we have this rotation this side, omega de R prime, par rapport à R vectoriel O prime M. It's now telling us about the rotation. As I told you, there's 2 types of movement. So the referential can be translating or it can also be rotating around it. So the vitesse de O prime par rapport à R is going to give us the translation movement. And then this other one, the omega, the R prime par rapport à R vectoriel O prime M is going to give us its rotation. And hence is born this formula for the vitesse. The vitesse du point M par rapport à R is going to be equal to vitesse du point O prime par rapport à R plus vitesse du point M par rapport à R prime plus omega R prime vectoriel, this omega de R prime par rapport à R vectoriel O prime M. So this one, know this formula. C'est une formule à retenir instead of deriving it every single time. Just know it by heart because you'll be working with it a lot. As I've told you, From now on, you will not be working with one referential. You'll be working with plusieurs referentials. So you are going to always use these principles of changement du référentiel. You have vitesse absolue, vitesse relative, and vitesse d'entraînement in most cases. In other simpler terms, you can denote it as this way. Instead of writing the full stuff, you can just write vitesse du point M par rapport à R égale V with a small a down here to show you that it's the vitesse absolue M. So instead of writing vitesse du point M par rapport à R, you can just write vitesse absolue du point M. We will know it's par rapport à R. Then we write vitesse with a small r outside. We'll know c'est la vitesse relative, meaning it's the vitesse of M with respect to that referential that's moving. And then you say vitesse with a small e down there, du point M. We will know that it is the movement of the mobile referential with respect to the referential that's fixed. And the absolute will give us now the total movement of the point that's been covered. Then we have quelques special cases. Lorsque R' est en mouvement de translation uniquement par rapport à R. So they're telling us it's only being translated, it's not rotating. So if it's not rotating, it means that term that had the angular vitesse is going to be equal to 0. That's why we have this here. The angular vitesse omega is equal to 0. That means in the vitesse d'entraînement, which was equal to this, we won't have the rotation. The repère won't be rotating. It will only be translating. So the vitesse d'entraînement will just be equal to this term here that gives us the rotation. The translation. I beg your pardon. Then, dans le cas où les deux origines sont confondues, I know in the diagram I drew, there were two origins. We had origin O and origin O', but sometimes the two referentials can have the same origin, okay? So if they have the same origin, it means one repère is not being translated with respect to another because they are all fixed to the same origin. So it can the only possibility of movement between the two referentials is going to be rotation. One will be rotating with respect to another, or it's going to be rotating around another, but it cannot be translated because they both have the same origin. If it's translating, it means one is moving away from the other and back, away from the other and back, but it cannot be the case because they have the same origin. So if one moves, it means the other one is also going to move because they have the same origin. So the only possibility of movement we are going to have is rotation, one rotating around another. So in a case where the two referentials or the three referentials or whatsoever referentials you're studying have the same origin, the translation is equal to 0. That means vitesse de O' par rapport à R égale à 0, and the vitesse d'entraînement is just going to be the rotation, and it's going to be the angular vitesse or omega de R' par rapport à R vectoriel O' M. If you guys are not stopping me, I'm going to take it as there are no questions. So if you get left behind, you don't get something, it's better you stop me and say, hold up.
Yeah, you need
that.
It wasn't clear on the last part of you can go up again.
No.
Again. The last formula, vitesse relative.
Vitesse relative, this one here. It's here?
Yes.
Okay, so as I was telling you, vitesse relative du point M is simply the vitesse of the point M with respect to that mobile referential, okay? I said we cannot take it as the total movement or the absolute movement because that referential itself is making some movements also. So we need to take into consideration those movements that repère or that referential is making. But we have to first of all take into consideration the movement of the point M with respect to that referential alone, and that's the vitesse relative. It's like I was telling you, I gave you the example of a person walking on the bus. So the person walking on the bus moves 2 steps and moves 2 meters in 1 second. That means the person has moved at a velocity of 2 meters per second. Now that 2 meters per second is only for someone observing that person on the bus, if both of them are on the bus, meaning that velocity there is with respect to the inside of the bus, of the referential, the bus, it's not going to be the same for someone observing you from outside, because from outside, the bus itself would have moved a distance. So it will appear as though the person moving on the bus has moved a longer distance than just 2 meters, okay? But for us to know exactly how much the person has moved or total, considering the movement the bus also made, we'll first begin by studying the movement the person made on the bus. That 2 meters the person moved on the bus, that's your Vites relative with respect to that mobile referential, which is the bus. And then afterwards, now we'll ask ourselves, how did the bus move? Then we'll say, okay, the bus moved so and so. And then for us to get the absolute movement, now we'll add what the bus moved and what the person moved, and we know how much movement or total in space that person would have made. So when we're studying 1.m dans R, we're studying it belongs to R prime, it belongs to the referential R prime, but we're studying it in R, and we know that R prime is moving with respect to R. So what we're going to first do is we'll study M in R prime. When we study M in R prime, we'll get our Vites relative. Okay, we'll study M in R prime, we'll get our Vites relative, and then after that, we will study the movement of R prime with respect to R, and then we add it to the answers we got when we studied the movement of M in R prime, and that's going to give us the total movement of that point. Are you clear on the Vites relative? It's just for studying the point M in the mobile referential. So it's not the total movement of the point M, but it's just the movement relative to that referential R prime.
Okay.
Okay, good. I hope it's clear for everyone. So we're just left with the composant, des accélérations, and we're done. We have 3 minutes. I don't know if it's going to be enough to explain to you guys, but it's just the formulas will be getting out. So you just have to know how to use formula de Bohr and also how to derive. So we found our Vites as a Vites absolue or Vites du point M dans R being equal to Vites du point O prime par rapport à R plus Vites du point M dans R prime plus oméga de R prime par rapport à R vectoriel O prime M. We found this. Now we want the acceleration, and we know acceleration is simply the derivative of the Vites. So what we're going to do is we're going to derive this entire expression here for us to get the acceleration. And as usual, we are finding, you ask yourself, I'm being asked to study the acceleration of what? Of the point M. To study it in what? The referential R. Okay, referential R. Then you ask yourself, in what referential has the Vites I'm studying been written in? This one, the first term, is been written in R. You see, it's in R. So this one, we'll just treat it normally. This one is in R prime. It's in R prime, the Vites du point M par rapport à R prime, or the Vites relative. It's in R prime. So now you have two referentials there. So you have a changement de referentiel. And when deriving that, you will need to use formula de Bohr because you have two repairs. You come to this one is unscathed. As we said, it's unchanged whether you're in R prime or you're in R. And then you come to O prime M. O prime M also belongs to R prime. And since we're studying acceleration in R, we are going to have to use formula de Bohr for this one also. So let's go on with it. We begin with this one, d'entraînement, la vitesse du point O prime dans R. It's not going to change anything. That's going to be gamma, the O prime dans R, because the derivative of the Vites is simply l'acceleration, which is gamma. So we just write it directly. And when we come to this second one here, it won't be as easy as the first one because this one is in R prime and we're studying it in R. So we need to use formula de Bohr. And we know when we use formula de Bohr, we first derive it in the referential it's been written in, or the referential it belongs in. So we'll derive it par rapport à R prime first of all, and then we'll introduce omega, the R prime par rapport à R vectoriel, that same angle you are deriving, that same vector you are deriving, which is V, Vites de M dans R prime, okay? And then this one, since it's R prime, it's just going to be direct and it's the derivative of the vitesse is just going to be gamma, going to become gamma, l'accélération du point M dans R' plus this term this side here, oméga de R' dans R vectoriel, la vitesse du point M, R'. So we keep this term there, we keep it like that. Then we move on to the second one. There's a bit of an error here. There's a bit of an error because normally you're supposed to work with this one first, this one. You derive omega dt vectorial O prime M. So this one is just supposed to be omega prime. You just write omega prime, that's all. Omega prime or omega point. What I meant to say was omega point because in Mécanique, we work with point. In analysis and algebra, that's why we break into prime. In Mécanique, we work with a point. So you just write omega point vectorial O prime M. Because for omega, it doesn't matter whether it's in R prime or in R, you just derive it directly. Then you come to this last one. The last one, we have omega vectorial de O prime M dt, derived in R. But O prime M belongs to referential R prime. O prime M belongs to referential R prime. And we're being asked to derive it in R. So what's going to happen there? What's going to happen is that we are going to use formula de Bohr, which is this one here. So it's going to be omega vectorial de O prime M dt in R prime from formula de Bohr, because O prime belongs to R prime, plus omega. This omega is this omega this side, omega vectorial. The omega that we'll get from formula de Bohr, vectorial, the vector we are deriving. I know they have gone on to expand it, but if you don't get confused, you can keep this as a factor outside, then you derive de O prime M dt dans R, you derive it first of all, you get your answer, then you can introduce this and you have something like this one. So when you have this, de O prime M dt dans R prime is just going to be la vitesse du point M dans R prime, okay? When you derive O prime M dans R prime, because O prime is the origin of R prime, you just have the vitesse of the point M in R prime. So you have omega vectoriel vitesse du point M dans R prime plus this double produit vectoriel that's coming from here. And now that we have expanded everything, we'll have our final expression for the acceleration. It's a bit longer. We'll have this one, gamma de O prime dans R, which we got here, plus gamma de M dans R prime, which was this one here, plus 2 omega vectoriel V, because we have omega vectoriel V de M dans R prime, and we also have omega vectoriel V de M dans R prime. So we add these two, it's going to give us that, plus the derivative of omega vectoriel O prime M, which is this term here. So you can just write omega point, si vous voulez, plus le double produit vectoriel there is coming from there, and that's that. That's the entire formula for the acceleration. But to simplify our work, we try and break down this formula into sub-components so that we can calculate them separately and not get confused. So the first thing to do is the first term this side, gamma de M dans R, the absolute movement is going to be called acceleration absolue. Like now you have the entire acceleration of the point M in R. You have studied everything. Then you have gamma du point M dans R prime, gamma du point M dans R prime, denoted by this being equal to the acceleration relative. So it's just like the acceleration of the point M relative to the referential R prime. That must be a referential. It's not giving us the entire acceleration, but it's giving us the acceleration of the point M with respect to that referential R prime. Then we have accélération de Coriolis, ou accélération complémentaire is equal to this term here, 2 omega vectoriel V du M dans R prime. I don't know exactly what it represents. I tried to Google it. I tried to ask the madam in school. I remember in first year, She didn't give me a proper answer. She just told me it's acceleration complémentaire. So maybe you guys will have some luck with your professors to explain what it represents in reality. Then finally, we have the acceleration d'entraînement. And as I told you, whenever you see d'entraînement, just know that it's the acceleration or it's the movement of one referential with respect to another. So if we have acceleration d'entraînement, it's telling us how the referential R prime accelerated with respect to the referential R, how it was accelerating. That's why when we add the acceleration d'entraînement and the acceleration relative plus the acceleration de Coriolis, which is the acceleration complémentaire, we get the absolute acceleration. It's giving you the acceleration of everything. And the acceleration d'entraînement, acceleration d'entraînement, you first have the translation, this one here, the O prime R, the movement of the origin O prime. It's telling you how fast, or it was accelerating. I don't know if I can say how fast it was accelerating or how much it was accelerating when it was being translated. Then the rest this side, they are representing its rotations. Okay, the rest this side are representing its rotations. So if it's just being translated, all these rotations here will be zero. So these terms will be out. And if it's not being translated, so if it's only being rotated, this one gamma O prime will be zero, and we'll just have the rotations this side. And that is the total formula for the acceleration en changement de référentiel. So you'll be working with, these are the things you'll be working with, because in most cases, you'll be having more than one référentiel. So you have to understand them. I know I was a bit fast. It's mostly because we've run out of time. It's past the time we're supposed to end the meeting. But try and go through the stuff and try and rewatch the video. And if you have questions, feel free to text me. People already text me to ask questions, shows that they are revising. So if you have any questions after you go through the stuff, you can ask your friends first of all. Then if they also don't know, then you can come to me and I'll be glad to respond to your questions. Are there any quick questions from what we've done now? Silence is golden, and it means there's no questions. And this marks the end of what we'll do in Mécanique du point. Yes?
Omega.
You're not so clear. I can't get what you're saying.
Yeah, I was asking.
I still can't get you. If you can manage to type it, just write it in the chat, because I think either your connection or my connection is very poor.
This acceleration need to be done again.
Okay, we can go through it next week.
Yes.
Or we can start doing questions, then it's going to become clear as we do the questions. Because we'll be using the same terms, so we can try to derive them before we answer, so that you guys understand, and then we go on. C'est bien?
Oui, c'est bonne idée.
D'accord. The meaning of omega. Omega is a letter in the Greek alphabet, and it's just used to denote the angular vitesse, the speed at which something is rotating. So that omega in that case is just representing how fast something is rotating. When we say angular vitesse or la vitesse angulaire, it's like the rate at which an angle is changing. And an angle only changes when something is rotating. So we can say this angle is changing at this and this degrees per second. That's going to be your vitesse angulaire, or your angular velocity, so to say. But omega itself is just a letter in the Greek alphabet. The way you say epsilon, epsilon is just a letter in the Greek alphabet used to represent a very, very small number in mathematics. And here in mechanics also, we use omega, just like gamma and just like V. Okay, gamma is just another letter in the Greek alphabet, and we are using it to represent the acceleration. So omega also is just a letter in the alphabet we are using to represent the angular vitesse. Is it clear, Mlengachev?
It's clear, thank you.
Okay, you're welcome. Vambi, are there any questions? Okay, if there are no questions, next week we'll do some questions, some TD questions. Yeah, in both sessions we'll just be doing questions. And don't forget the assignment I've given you guys. And don't forget you're working in groups of 3s. You're supposed to send your names to Ruben, but you guys didn't send your names. So do so, send your names to Ruben, and I guess we'll advance from there.
At hand, we just have about 4 groups.
4
Those are
groups.
the guys. Yes.
That's like 12 people, but there's more doing mechanics than that. So the others, let's send, please. And I wish you a good afternoon. Enjoy the rest of the day. On se verra la semaine prochaine, Inch'Allah.